Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing using vectors to simplify notation and calculations in the Cartesian plane. This video is produced for Ohio University Math 3110-5110, College Geometry. The topics that I'll be discussing in the video are triangle inequalities, the vector space R2, and using vector notation and calculations to simplify geometry. The material for this video is from section 3.1, titled An Alternative Description of the Cartesian Plane, in the book Geometry, a Metric Approach with Models. The corresponding homework is this short collection of exercises from the book, and then you'll also have some custom problems. Let's recall some important things from section 2.1, the definition of abstract geometry, which is a set of points and a set of lines that satisfies these axioms. An incidence geometry is a set of points and a set of lines that qualifies as an abstract geometry and also satisfies these additional axioms. The Cartesian plane is the set of points, that is, the set of ordered pairs of real numbers, and the set of lines consisting of these vertical lines and these non-vertical lines. So two flavors of lines in the Cartesian plane with different looking descriptions. It's a fact we discuss in Chapter 2 that the Cartesian plane satisfies the definition of incidence geometry. So it is a model of incidence geometry. We discussed in Chapter 2 this procedure for finding the Cartesian line passing through two distinct given points in R2. You had to first figure out if those points had the same x-coordinate or different x-coordinates, and the line then that you built had different descriptions depending on those two cases. We had an important definition from section 2.2, the definition of a distance function. It's a function on a set S that satisfies this set of three requirements. We considered some examples of distance functions. We had the absolute value distance function on the set of real numbers, computed this way. You compute the distance between two real numbers just by computing the absolute value of the difference. And then we had the usual Euclidean distance function on R2, and we had the taxicab distance function on R2. We had the definition of a ruler for a line. This gets used in the situation where you have an incidence geometry and you have a distance function on the set of points. To say that f is a ruler for a line L means this. F is a function from L to the real numbers that satisfies these requirements. Has to be a bijection and has to agree with the distance function in this way. This equation is called the ruler equation. We had a definition of metric geometry in Chapter 2. A metric geometry is a triple set of points, a set of lines, and a distance function. The set of points and lines has to qualify to be called an incidence geometry, and furthermore, the triple has to satisfy this requirement, that every line has a ruler. That's called the ruler postulate. We discussed a few examples of metric geometries in Chapter 2. In this video, we'll be most interested in two, the Euclidean plane and the taxicab plane. Both of those have as their underlying incidence geometry the Cartesian plane. We had rulers for our geometries in Chapter 2. Now, in the geometries involving the Cartesian plane, remember we had two flavors of lines, vertical lines and non-vertical lines. Well, it should be no surprise that we have two flavors of ruler for those lines, the standard ruler for a vertical line and the standard ruler for a non-vertical line. Finally, some new content. I want to talk first about triangle inequalities. I want to talk about the triangle inequality for the absolute value. It is this. The absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. The proof of this is straightforward. It really, on its own, would not be worth putting in this video, but I put it here anyway. I'll let you read it. It's worth putting this in because we're going to encounter some other triangle inequalities whose proofs are not so simple. There are other things called triangle inequality, as I just mentioned, and they're not even necessarily true. So here's a definition of what we'll say is the triangle inequality for distance functions. So we'll say that a distance function on a set P satisfies the triangle inequality if this inequality is always true. The distance from A to C is less than or equal to the distance from A to B plus the distance from B to C. Now, from way back, you've probably heard something like this, that the shortest distance between 2 points is the length of the line segment that connects those 2 points. That's embodied in this inequality. That can be visualized in the following way. So in that triangle, the shortest distance between A and C is the length of that blue segment. That corresponds to these terms up here in that inequality. Let's go on. It's easy to show that the absolute value distance function satisfies the triangle inequality for distance functions. Remember, this is the absolute value distance function on the set of real numbers. It's this function defined this way. So let's show how it satisfies the triangle inequality. First of all, let's build the left side of the triangle inequality. The left side is this, the distance from A to C. Well, there's the left side. Here we just use the definition. We use the definition of the absolute value distance function. And then here we use a trick. We subtract and add something. So the result of that is no change at all. We've just inserted a 0 within that expression. But that enables us to use the absolute value triangle inequality. That's that triangle inequality that we proved was true on the earlier page. And then finally, we use the definition of the distance function again. And that's the proof. We have the right side of that triangle inequality appearing there. Now, what about other distance functions? I mentioned that not all distance functions satisfy that distance function triangle inequality. You will show in your homework that the taxicab distance function and the max distance functions on R2 both do satisfy that triangle inequality. Those proofs are done in a manner similar to this proof that we just did. At some point, you'll use the trick of adding and subtracting something, and then following that, you'll use the absolute value triangle inequality. But not all distance functions satisfy the triangle inequality. Indeed, in your homework problem 3.19b, you'll show that a new distance function called d subscript f does not. So an obvious question is, what about our most familiar distance function, the Euclidean distance function? Does that satisfy the triangle inequality for distance functions? Here there's a typo. If you attempt to show that the triangle inequality is satisfied using the formula for the Euclidean distance function, the computation gets very messy very fast. It turns out that computations can be made easier by using computations involving vectors. That and some other reasons lead us to study the vector space R2. So recall that points in the Cartesian plane are elements of the set R2. That is, they're just ordered pairs of real numbers. There are no operations involving points, aside from the distance function on the set of points and the coordinate functions on the set of points on a line, that is, ruler functions. You cannot add points to each other, and you cannot multiply points by numbers in the Cartesian plane. But in the vector space R2, you can add ordered pairs of real numbers, and you can multiply an ordered pair by a real number. That's called scalar multiplication. So here's the definition of the vector space R2. Now, a vector space is a triple. It's a set, an operation of addition, and an operation of scalar multiplication. So if I want to sell you a vector space, I have to tell you what the set is, and I have to tell you how the addition works and the scalar multiplication works. So that's here. The rest of this is some other sort of additional stuff. What's called the inner product of two vectors is denoted by this symbol, and it's computed using this computation. So that's what you would have called before in some other courses maybe the dot product. And what's called the norm of a vector is denoted by this symbol, and it's computed using this formula, which boils down to this. Basic properties of the vector space R2 are articulated in this proposition. 9 different properties. Now, each of these properties is fairly basic. This one is commutativity of vector addition. This is associativity of vector addition. And then there are some things that look like distributive laws for vector addition and scalar multiplication. You should be able to prove this proposition. Its proof amounts to just straightforward calculations that verify each property. In other words, you just build the expression that this represents, you build the expression that this represents, and you show that they actually mean the same thing. But there are some more sophisticated properties of the vector space that are articulated in the book. One is the Cauchy-Schwarz inequality. It's this inequality. For all vectors a and b, if you take the inner product of a and b and then take the absolute value of that inner product, so that's going to be a real number, that's going to be less than or equal to the number that you get by taking the norm of a, the norm of b, and multiplying. The authors give a nice proof of that on page 45 of the book. Another sophisticated property is not presented as a proposition of the book, but it is worth presenting here in a nice green box. I'll call it the triangle inequality that's satisfied by the norm for the vector space. Here it is. For all vectors a and b, this inequality is true. The norm of a plus b is less than or equal to the norm of a plus the norm of b. The authors do give a proof of this triangle inequality on page 46, but it's within the proof of some other thing. So they don't present this as a proposition. They don't present a proof of it as a proof of that proposition. But they do end up proving that this statement is true within the proof of another proposition. So I won't present these proofs here because they're done nicely in the book. But in a class meeting, we will discuss some particular examples of vectors a and b that illustrate these inequalities, and you'll do the same thing on a quiz. The point of introducing the vector space aspect of R2 is subtle. We're still interested in points as elements of this set R2. Remember, in the Cartesian plane, you can't add points together. You can't multiply points by real numbers. But it turns out that some calculations involving points are made simpler if we use the operations of the vector space. So here's an example where an operation in the Euclidean plane, metric geometry, corresponds to an operation in the vector space. This proposition says, for all a and b in R2, this equation is true. So the Euclidean distance between a and b is equal to the norm of the vector a minus b. So on the left side of this equation, we have a computation from the Euclidean plane. On the right side of this equation, we have a computation from the vector space R2. Those are two different worlds. So this proposition, although it's simple looking and simple to prove, is actually important conceptually. The proof is very simple. If you build the expression that the left side represents, it turns out that's just that. If you build the expression that the right side represents, it's just that same thing. Now, that equation is certainly interesting, but you might notice that it doesn't really seem to offer any real advantages. The left and right sides of the equation are simply two different ways of denoting the same messy calculation. That thing. But now let's return to a question from earlier. We had this question, does the Euclidean distance function satisfy the triangle inequality for distance functions? Well, it turns out that we can give an answer now. The proof is wonderfully simple. We can write down the left side of that inequality, the distance from A to C, and then we can use this proposition, proposition 3.1.3, to replace that symbol with this symbol. And then we do that trick again. We subtract and add b, which doesn't change anything. Now we get to use the fact that the norm satisfies the triangle inequality. Remember, I said that this was not articulated as a proposition in the book, but it is proven in the book, and I'll show you where it's proven. It's actually proven in the book's proposition 3.1.6 proof. So here we're using the fact that the norm satisfies the triangle inequality. And then here we go back to using distance function notation. So we use proposition 3.1.3 again. We can also use vectors to describe lines in the Cartesian plane. Now recall that in the Cartesian plane, if you're given two distinct points, the description of the line through those 2 points depends on whether or not A and B have the same x-coordinate. But using vectors, we can give a description that works for all cases. So here's how it works. Given 2 distinct points, the line AB can be described using vectors as follows. The line AB is that messy expression. Now that expression is what is presented in the book. The letter x is not really necessary. I like this presentation better. Line AB is vector A plus t times vector B minus A, where t is an element of the real numbers. So for example, let's let A be the point 35 and let's let B be the point 59. Use vectors to describe Cartesian line AB and simplify the result. Well, we just go up and get this formula, the set of all A plus t times B minus A, and we just build that. The set of all A plus t times B minus A. And that's it. There's our description of the line. Now that can be simplified. It can be simplified to this form. Now you might recognize that. That's the parametric form of the description of a line. The set of all points that have x equals 3 plus 2t and y equals 5 plus 4t, where t is a real number. We can illustrate that fairly easily. So there are our points. The line they lie on we could draw as a black thing. And vector B minus A we could draw as a blue thing. Vector B minus A starts at A and ends at B. Vector A starts at the origin and ends at A. So you could think of this prescription as or this one, as telling you to do this. Go to point A, that's go to that spot, that's that green vector, and then add any multiple that you want, any multiple of the vector 2, 4. That'll be adding any multiple of that blue vector to that green vector. The result will always be along this black line. Let's go on. Now there's a lot of subtlety hidden in the notation of that symbol. Starting with these ordered pairs representing points, you think of those ordered pairs as vectors in the vector space. And then you perform vector addition. That's there to get this new vector, 5, 9 minus 3, 5. And then you perform scalar multiplication to obtain this vector, t times that old vector. And then you perform vector addition again to obtain this new vector. And then finally, you think of that result as a point. You go back to thinking of ordered pairs as points. Now there's less subtlety in this symbol. Remember that I simplified this expression to write it in this parametric form. In this symbol, the multiplication and addition are real number operations. They're not vector operations. So this whole thing is just a point. It's just a set of points. It's just that the description of what's inside the points involves this letter t. So conceptually, this parametric form is sort of simpler in that it's more primitive. It doesn't involve vectors. It just involves real number calculations. But conceptually, on the other hand, in a different way, this is simpler because you can see there's your point A showing up there, and there's your point B. So you can see how this thing was constructed. You can see the original points A and B showing up in that description. Example B. Let A again be this point 3, 5, and this time let C be this point 3, 9. Use vectors to describe Cartesian line A, B, and simplify the result and illustrate it. Well, we just build that same kind of form. There's our point A, and there's our point C, interpreted as vectors, and we build that expression and we're done. That's the Cartesian line expressed using vectors. Now we can simplify that to a parametric form, and we can illustrate this as we did in the previous example. So the idea of this prescription is that you travel along this green vector first and get to A, and then add any multiple that you want, any multiple of this blue vector to that green vector, and the resulting vector will be somewhere on this vertical line. Now notice that in part A, we had a non-vertical line, and in part B, we had a vertical line. However, that distinction played no role in our construction of the descriptions of those lines. We simply built this expression, and the result was a perfectly valid description of the line in both cases. Now, vectors can also be used to define rulers. So here's a proposition. If LAB is a Cartesian line, then this thing, this function from that line to the real numbers defined by that formula, is a ruler for that line. Now, the proof that that ruler really does define a ruler is presented in the book, and I won't discuss it here. But it's worth exploring the vector description a bit. We'll see that although the vector description of a ruler is easy to write down, just as the vector description of a line is easy to write down, the resulting ruler is not so convenient to use to actually find the coordinates of a point. So for example, let's let A be the point 3, 5, and let B be the point 5, 9. Use vectors to describe a ruler for Cartesian line A, B. Now you'll recognize those points. We used vectors to describe that line earlier in the previous example. Well, here we go. We just use that prescription, build that, and it looks like this. We put the ordered pair for A there and there and there. We put the ordered pair for B there and there, and that's our description. Now that can be simplified though. First of all, we can do this subtraction and obtain this new version. And that can be simplified because we have this, the norm of that vector. That turns out to be the number 2 square root of 5. So our ruler can be simplified further to this. And that can be simplified to this. So that is sort of a parametric presentation of the ruler. So fairly simple to build this thing. Now using that ruler, let's find the coordinates of point P that lies on that line. Well, first of all, we have to find the value of t. Since P lies on that line, P must be of the form 3 plus 2t, 5 plus 4t. That's from earlier when we described that line using vectors and we arrived at that parametric description of the line. So we have this equation that says this point, 4, 7, has to be obtainable by this calculation. So we can use that to figure out the value of t. T has to be the number 1/2. Now that we have the value of t equals 1/2, we can use that to find the coordinate. So the coordinate of p, that is the coordinate of this point, which has a 1/2 in it, is given by this calculation. The 1/2 goes in front of that 2 square root of 5, and we just get square root of 5. Now using that ruler, find the coordinate of point Q, 6, 11, that also lies in that line. Well, again, we have to first find the value of t. We have to set 6, 11 equal to this thing. Again, that's the parametric form of the line. And when we solve for t, we find that t is equal to 3/2. So that means that q is written in parametric form this way. The 3/2 shows up in that parametric description of q. So the coordinate of q is that number 3/2 times that number 2 square root of 5. So we get that result for the coordinate of q. Now let's check this result. Let's use the coordinates f of p and f of q to build this, see what we get. Well, when we build that using those results that we got, our answer is 2 square root of 5. Now let's compare that with the result of just computing the Euclidean distance between p and q. When we do that, compute the Euclidean distance, we get 2 square root of 5. So using this thing that we are claiming as a coordinate function to compute this expression, we get 2 square root of 5, and that's the same as the result of computing the distance. So we see that the ruler equation is satisfied. Now there's a typo here. So the remark I want to make is that we can see that this vector form of the ruler is simple to build, but it's cumbersome to use it to actually find the coordinates of a point, because we have to first find the value of t. But even though it's cumbersome to use that ruler to find the coordinates of a point, that ruler is handy from a theoretical standpoint. Here's the first example of a situation where that vector description of a ruler is handy. It turns out that it's a special ruler in the following sense. Consider two given unique points, A and B, in R2. They determine a line AB. There's a typo here. So they determine a line in the Cartesian plane, and we have this way of building a ruler using vectors by this formula that describes a ruler for that line AB. Let's find the coordinates of points A and B using that ruler. Well, to find the coordinate of point A on that line, we have to first find the value of t. Well, notice that A can be written this way, and if we solve that equation for t, we find out that t is the number 0. So the coordinate of A is that t times that quantity, so the coordinate of A is 0. To find the coordinate of B, we must also find the value of t that works for point B. Well, let's build this equation. B is on that line, so B has to be of the form A plus t times B minus A. If we solve that for t, we find that t is equal to 1. So that means that the coordinate of B is this quantity, which is a positive quantity. So we see that the ruler for f will have the property that f of A is 0 and f of B is positive. In my videos, I've called this kind of ruler a special ruler for points A and B. The book calls this a ruler with A as origin and B positive. Now, remember from section 2.2 of the book that a lot of work went into building a special ruler using section 2.2 techniques. And actually, I guess this is section 2.2 and section 2.3. By comparison, we were able to build a special ruler using a vector description very quickly. This is one example of a situation where the vector description of rulers is handy from a theoretical standpoint. We'll see other situations where the vector description of rulers is handy in coming sections. Well, that's the end of the video. Thank you.